In this segment, we're going to talk about some of the approximations that we can make for compressed liquids. So let's kind of recap what we've got so far. We've got some rules that we can use to determine what phase our substance is in. Let's look at that saturated region real quick to recap. We can calculate the specific volume based on the quality, and there's similar relationships that apply for calculating internal energy and enthalpy for a substance in the two-phase region. Now we're going to focus specifically on this compressed region. Now, if you have your tables, if you have your compressed tables handy, you can absolutely use those. But you'll notice that the compressed tables that you have, you've only got one sheet of data. And the data that's tabulated, you only have data for a pressure range of 25 bar to 300 bar. And if you're outside that range, it doesn't necessarily mean that you're not compressed, it just means that you don't have data for that. So you can either extrapolate, which could cause you to have a lot of error in your analysis depending on how close you are to the data that's actually in that table, or you can make an approximation, and that's typically what we do. We make an approximation. So if we look at a TV diagram, and this is that dome, that's the liquid vapor dome, and all those little lines going across are lines of constant pressure. I'm going to look at a small segment of this TV diagram and zero in on that saturated liquid line. So here I am, I've zoomed in, and now let's get our bearings one more time. This line all the way to the right, or the curve here, that's the saturated liquid line. That's part of that vapor dome. Now, this blue dot represents the state of your substance, of your compressed substance. So it's out there in the compressed region. And then there's a little, you'll see there's a red dotted line that goes through that, and that is the line of constant pressure. Now, if I'm wanting to make an approximation about what that specific volume is of that blue dot in my compressed region, I could approximate this as the V sub F value at that given pressure, at the pressure of my compressed liquid. So, anywhere along that red dotted line, the pressure is constant. So that open circle up there at the top has a specific volume of V sub F at that pressure. But you can see that that's a pretty sizable error. It would be nice if we can get a smaller error. So now we're going to look at the V sub F value at the temperature of the compressed liquid. So anywhere along that horizontal line right there, of course, temperature is constant, right? And you can see there that the error associated with making that approximation is very small. And so that's what we do. We approximate for a compressed liquid at a given temperature of pressure, we approximate it as V sub F at the temperature, not the pressure, the temperature. So that's just something that you'll have to get in your head. This is also an equation that's given to you on your equation sheet. You just have to remember to use it if you need it. So just to kind of recap, we can approximate values for compressed liquids. We can do this for specific volume. You could also make a similar argument for internal energy. And we also have an approximation for enthalpy. You could see that it looks really similar, except it's got that second term over there. And the reason that it's different, this is, if you look in your book, you can see how they get this, but this is taken from the approximation for internal energy, the U sub F at T, and the definition of enthalpy, which is U plus PV. Now, often that second term right there is very small, and so it's often ignored, but just be aware that it is there. All right. Well, that's it for approximations for compressed liquids, and thank you for watching.